Good morning, everyone. This is Sundar. Sorry I couldn't make it to class today. I put a recording together, time for this class. Let me know how you are able to follow through it. So, we'll continue our conversation about the use of constraints in designs. In the previous class, we looked at the situation when you had a single objective, two objectives, or more than two objectives to be able to work with a design function, and you could have several constraints. So in the first case, you would rank and then use property index. In the second case, you would construct some kind of a trade-off plot when you had two objectives, and that was connected by the use of the penalty function. And then finally, you would have create an exchange constant map if you had more than two objectives. So you'd construct multiple trade-off plots for the various performance indices P's. Let's focus on the situation where you have a single objective and many constraints. Let's look at the tie rod situation again, where the length is L, the load is in tension, it's supported by load F. You want to compute the minimum weight without failing, and in that case, the constraint is a strength, or you want another situation where it can extend elastically by more than delta. So the constraint on stiffness is F by delta. Let's look at situations where we are able to derive those performance equations for each mass M1 and M2 based on the constraints. Then we'll look at deriving material indices, and finally we'll come up with a coupling equation that links those two material indices so that we can make plots. So this is a geometry that we are looking at. It's a cylindrical tie rod, and force F is applied in tension. The rod is of length L, the cross-sectional A is a free variable as we've always seen. And so if you look at creating that table, the function is specified as a tie rod, constraints are given. On the one hand, L and F are specified, and we have to say that F should be less than the yield strength, and then F by delta, which is the stiffness, should be specified as well. We are free to use A and then the choice of material, which is the purpose of creating those different plots. So we start out with the familiar point of for the cylinder of length L and cross-sectional A, which will have a volume of A times L. Then if it has a density rho, then we will have a mass that we can compute. So the objective is to minimize the mass AL rho, and the two kinds of constraints. On the top, you have something based on the stiffness. If you take basically stress is equal to epsilon times E, and the stress is F by A, and then epsilon, the stiffness, is delta by L, E, the Young's modulus, is provided. So if you rearrange those terms and then you eliminate A in the equation for minimizing mass, you will get one type of a mass. Secondly, on the strength constraint, where yield strength should be at maximum F divided by A. If you rearrange terms, A will be F divided by sigma Y, and then again the mass can be the objective function to be minimized, and we replace A in this equation. So A is area, L is length, rho is density, F by delta is the stiffness, E is the Young's modulus, and sigma Y is the yield strength, or the elastic limit for these set of considerations. So now what is M1 based on the first constraint? What is M2 based on the second constraint on the strength? If you go through replacing A into this equation for M, first you will, based on the stiffness constraint, you should get a mass that is L squared times F over delta times rho over E. So L is the geometric constraint, F by delta is the functional constraint or functional index, and rho by E becomes your material index. Right? So the second constraint based on strength would, if you rearrange terms by eliminating A, which is a free variable, you will get L times F times rho by sigma Y. And so again, you have a product of geometry, function, and material indices. Compare this with what we had seen in class during the lecture 13, where we ended up basically looking at the objective of M equals to A times L times rho. We used the stiffness constraint and the strength constraint, and we came up with these performance equations to compare three different kinds of materials based on plotting these two material indices, rho by E, which is capital M1, and rho by sigma Y, which is capital M2. So pretty much doing the same thing. We're just using a different set of terms for the stiffness and the failure load. So based on what we saw from the material indices in computing the two different masses, you get two different material indices. And so one material index is rho over capital E, and the other one is rho over sigma Y. What do we do with these material indices? Basically, we use them as two axes, right? In order to do that, first we set M1 equals to M2, and for that we can go ahead and derive the coupling equation. What is the coupling constant over here? It's L over delta, as you can see in that equation. So if you have a log-log plot of the two material indices, then you can have basically a bunch of equations with different intercepts of L over delta. So first let's create the plot. Okay, so in the first case, for the y-axis, you have density over yield strength, and in the second case, you have density over the Young's modulus. Because of the difference in numbers, we modify the x-axis a little bit. And so you end up having this plot, and so you'll see that on the top of the plot, you basically is dominated by ceramics, bottom corner is dominated by metals, some carbon fiber reinforced plastics, or some composites, and the polymers are right here on the top right hand corner. Okay, so depending upon varying the intercept, you'll have different coupling lines. Let's specify two coupling lines, one where L over delta is 1000 and delta over L is 10 to the power minus 3, or a second case when L over delta is 100, and so delta over L is then 10 power minus 2. So if you go back and revisit those plots, you have these two different constraints. It'll be good to try these out on EduPack to apply different slopes. And the main thing is for the first constraint, where L over delta should be at least 1000, you end up having a bunch of ceramics dominating the scene, because we have to take the minimum masses, right? When M1 is set equal to M2 in terms of the two masses. So we are looking at some things in this kind of corner. And in the second kind of a constraint where L over delta is 100, or the reciprocal is 10 raised to minus 2, you will come across carbon fiber reinforced plastics, aluminum alloys, titanium and magnesium alloys. Think about what do you do with ceramics in tension. They will have flaws. It doesn't do very well, does better in compression, right? So what is the meaning of these recommendations? The one constraint we would have basically, if these two are reversed a little bit, okay, you would have boron carbide and silicon carbide, and the second one you would have carbon fiber reinforced plastics, titanium, aluminum, magnesium alloys. And this is the best choice, really, if you want ductility and toughness. Okay. It turns out that these ceramics work out great as fibers, and oftentimes silicon carbide fibers are mixed with aluminum alloys to make tie rods. And so that is often used in automotive applications, so that you get a little bit of the best of both worlds. When you have a small cross-sectional area, as in the form of fibers, then you can take advantage of the stiffness of the material, and you can eliminate flaws in tiny cross-sections much better, because of the fact that you have a different synthesis route and you're really not densifying these fibers as you might for other ceramics in the bulk. So this is one type of an exploration where you have multiple constraints and you have one single objective, which is minimize mass. Let us look at one more variant of the same